The ongoing search for Planet 9 continues to heat up as evidence accumulates that a large planet exists somewhere in the outer solar system. But where? Predictions of what Planet 9's orbit is like could very well be the key in actually locating the planet, leading to several different approaches in figuring this out. My guest today has worked out one such approach, that of looking at the question from the perspective of engineering physics, taking us one step closer to locating Planet 9, if it indeed lurks out there in the far reaches of the outer solar system. Robert Finch received his BS and MS in Applied Math from Oklahoma State University and a Master's of Engineering and Operations Research from Cornell. He is a retired senior engineer at IBM Federal and then Lockheed Martin, and his interests include Planet 9, breakthrough energy technologies, and the physics behind it.
Welcome to Event Horizon with John Michael Godier.
Robert Finch, welcome to the program.
Thank you. Thank you for having me.
Now, Robert, for several years now, we've had this sort of specter out in the outer solar system that some object seems to be affecting the orbits of asteroids or objects deep out in the outer solar system. Now, we've accumulated quite a list of these objects that seem to have altered orbits by some large gravitational source. Your work looked into trying to figure out attributes of Planet 9, as it's called, from those orbits, torques, and things like that. Could you explain briefly what that means? What did you look at that led you to conclude certain things about this potential planet?
Okay. Let me just start at the beginning. What we did, we had done some reading early on with regard to some of the papers that had come out following the discovery of Sedna. And we really didn't have any data to work with. In the past, the Naval Observatory tried to do some things with the perturbations of Neptune and Uranus, but people don't even think that those are actual perturbations now. So when the Brown Batygin paper came out in 2016, we were delighted because there was some additional information. So we thought, this is not a horribly difficult problem to put together a model for if we make a couple of simplifying assumptions. So that's what we did. We started looking at the system as a torque-driven system. If you have a planet that's in orbit around the sun, and you have another large planet that is in sort of a non-circular orbit around the sun, then it induces a torque on the first. If it's a small body like an asteroid, that torque is obviously pretty substantial, and it will move the object in a way that changes its orbit in an unusual way. What we found, and we developed equations of motion for that, let me call them asteroids. They're trans-Neptunian objects, but a couple of them are planetoids. So I'll just collectively call them all asteroids. I'll just be using that term from now on. So basically what we saw was in the model was that the torque tries to drive each asteroid into the orbital plane of Planet 9. In other words, it tries to make the two planetary planes coincide. The other thing that it tries to do is it tries to move the asteroids in azimuth. And even in Brown's original data, all of the asteroids fell within about a 95% angular spread that he saw. We opened that up. We actually used more objects than he used. We used 12, but we actually did the analysis for both 6 and the 12, the original 6 that Brown used and 12 that we used. Going back to the torque again, in the azimuth direction, torque moves the asteroid's planes to change its orientation in space. What we found was that there are two groupings where those angular orientations ended up. Not necessarily ended up, it's still an ongoing process. But there were two collections of azimuth orientations which were absolutely dominant. And what we believe is happening there is that the asteroids are actually aligning with the approach and retreat paths of Planet 9. And we have a lot of analysis as to why we believe that, but it's very clear that that's what we saw, or that's what we're seeing in the data. And so what we did is we did an analysis using that gravitational torque model to develop initially the plane that Planet X, or the orbital plane that Planet X should be in, or Planet 9. We use Planet X in the paper, so I'm going to be switching those back and forth. And also the azimuth orientation. The azimuth orientation, like I say, should be right in the middle of those two clusters that we found. And that's what the torque model predicts.
Now, you mentioned briefly the perturbations that seem to be evident, at least in the past, of Uranus and Neptune. And this is an old idea. People have known that something was a little bit wacky there for over a century. Do you think that's real, or do you think that's explained? And my sense was that it was explained, but maybe not so satisfactorily.
That portion of the problem we didn't look at because we assumed that it was basically a non-issue, and we weren't using that as data anyway. I believe the astronomy community believes it's explained away. I don't know whether that's really true or not. I believe that it's accepted that it is. And so I looked at what the Naval Observatory did, and Robert Harrington was heading up a massive study effort to try to find Planet X. It was called Planet X then. And he was using the perturbations to create a math model and a simulation to try to find it. So back then, it was before the astronomy community had decided that it was basically an error in the mass. So I can't really tell you much more than that. We didn't use that information in any way, shape, or form. We only used the asteroid information.
Now, there was also, as I recall, too, that we've used some of the space probes, I think Pioneer, to try to see if there was any sort of gravitational perturbation. But this thing would be so far out that you probably wouldn't see any effect as far as this thing would be, right?
Yeah, as a matter of fact, that was going back to Harrington again. He was really the originator of that because he was heading up the effort to try to find Planet X. And you're right, they did use Pioneer 10 and 11. And there was some degree of belief that they had gotten some sort of a funny signal, but it was never confirmed. And whether they actually detected anything or not, I don't think there's enough evidence there to conclude one way or the other.
Now, your work shows that Planet 9 is distant at an orbit of, or at a period of 3,500 years, which is significantly less than Batigan and Brown's estimate, which I think was like 15,000 years, something like that.
Right.
So what constrained that down? What leads you to believe that Planet 9 is on a shorter period than that?
Okay. That's a very good question because this is really the key. You homed right in on it. The issue is conservation of momentum. We had three assumptions in our model. We assumed that the mass of the inner planets were concentrated at the sun. In other words, all of this activity was happening. The activity of Planet 9 was basically acting as if the inner planets were concentrated at the sun. The asteroids don't interact with one another, and then the third one is that the solar system's angular momentum is conserved. That means it's constant. Now, let's assume for a minute, I think the easiest way to understand this for me is that assume for a minute that Planet 9 is in an orbit by itself around the sun. Nothing else is there. Now, we want to keep the angular momentum constant. when we make a certain injection. We want to put all of the asteroids in however they would fit in their normal orbits, wherever they are, instantaneously, and ask the question, what has to happen to the angular momentum of Planet 9 to keep it constant? Well, it's pretty obvious. What has to happen is that the perturbation that you introduce into Planet 9's angular momentum, has to be equal and opposite in sign to the collective angular momentum of the asteroids. That's point one. And once you make that assumption, then you say, well, how does the angular momentum of Planet 9 change? Well, what happens is it doesn't change in magnitude because there's not enough mass in those asteroids to change something that's fairly large. It changes in orientation. That says that what's known as specific relative angular momentum, that's the angular momentum per unit mass, that value as a magnitude doesn't change. What changes is its orientation. And with those two facts alone, you can compute the relative angular momentum of Planet 9. And once you do that, you're home free because you can get all the other parameters from Kepler's equations.
Such as the orbital period and even the mass, right?
Not the mass. Not the mass. The mass is another question. Well, I have to back up a little bit. You have to compute, there's a trick you have to use to compute the eccentricity, and the mass is a completely separate calculation. It depends on something else, which I can walk you through too, because in one of Batygins' lectures, he made a statement that said they never actually computed mass. They estimated it using the simulation. So at any rate, once you get the relative angular momentum and eccentricity, you can compute everything else. But you do need eccentricity. Eccentricity actually comes out of the orientation of the two clusters, the two angular cluster spreads of the asteroids. So when you're looking into space and you see these two clusters, then there's a relationship between that angular cluster and the eccentricity of what it is that's doing the clustering. And we go through that explanation, that calculation. And then you can get the eccentricity. And once you have the relative angular momentum of Planet 9 and its eccentricity, you can get everything else except mass.
Now, you came up with a number, though, 8.5 Earth masses.
Right.
Now, what could this planet be like? Do you favor a model of, as I recall, Batygin and Brown advanced, that this may be a sort of a Jupiter core or protoplanet that was kicked out of the inner solar system early in the solar system's history? Or do you favor something like a capture model where this could be an interstellar object that the solar system managed to somehow draw in? Does your work give you any insight into that question?
Our work really doesn't. I've read a little bit on that, and I have to tell you, not being an astronomer, I'm on pretty thin ice here, but most of what I've read talks against the capture model in favor of some sort of a chaotic disturbance in the primordial mass circling the sun, and that sometimes that comes together not all the way into the sun, but actually out extended. But I can't really say any more than that. I'm really not fluent with this level of astronomy.
Now, you mentioned, and in fact, the title of the paper is using engineering principles rather than just standard astronomical principles, related though they would be. What is the difference in approach here on that? Thinking about this from the perspective of engineering rather than just straight astrophysics. What was the difference?
Well, I think the main idea is the whole torque model. from once you assume the torque model, you can actually generate the equations of motion of an asteroid, and we've never seen that anywhere. So it would be really nice if the community can take a look at it and see if we're on target here. But we believe that the torque model is what allowed us to generate the equations of motion for the asteroids. So that's the primary thing. But of course, a lot of this is classical. Once you've gotten a certain number of parameters estimated, then you can use Kepler's equations to essentially figure everything else out. You've got to have the relative angular momentum and the eccentricity. And once you do that, then you're essentially in the world of astronomy. But the main thing I think we brought to the table was the fact that we could show how the angular momentum has to change over time. And from that, we could figure out what the relative angular momentum is, and then go into the world of astronomy to get the rest of the parameters.
Does the sampling of asteroids that you guys looked at, does this give us any clues on where we might point the telescope to try to find Planet 9?
Yes. But we used the 6 reference asteroids that Brown and Patigan used, and we also found that there was a very severe data bias. Sedna is in that collection, and Sedna is huge relative to everything else. So it's driving the model askew. It did for us. In fact, it drove our model askew in the same way that it drove Brown's model, because we compared numbers with them with regard to the orbital planes, and we're very close. We're very close. Then we put in 6 others, and we opened up the spread. Instead of 95 degrees, which Brown had in his azimuth spread for asteroids that he would consider, we went out to 125 degrees, and we were able to find 6 more asteroids. So we had a sum total of 12, and that defeated Sedna's data bias somewhat, quite a bit actually, and it changed the numbers more so than the difference between our original numbers and Brown's numbers. So we were pretty excited about that, but the numbers were still not drastically different.
This is sort of all part of a growing body of evidence that Planet 9, in whatever form we find it, seems to exist, and the the meter seems to be going further and further towards this object existing. Gut feeling, is it really out there, or is there still a possibility that there may be a misinterpretation?
I think it's out there, and the reason why I think it is because not because of one indication, but because of several. We have strong agreement in the planes. All 12 of those asteroids that we picked all fell within a standard deviation from the plane that we assumed being the average of those. It was, the standard deviation was only 14 and a half degrees. The azimuth difference was only 15 and a half degrees. Now that couples well with the fact that we had the relative angular momentum, which I think I mentioned this earlier, but the relative angular momentum of all of the asteroids is very close to the same number. It's very close. This was very surprising because nobody's noticed this. And that's not just with the 6, it's with all 12. So we have very strong correlation between the dynamic motion of all of these asteroids. They're being herded together in angular momentum. So it's pretty interesting, and it's hard to explain any other way that you would have this wide collection of objects that are in so close agreement. The other thing we found was that of the 12 objects we chose, 4 of those 12, and we didn't know this at the time, 4 of those objects are in mean motion resonance with our Planet 9 orbit. That means that some integer multiple of the period of 1 is equal to another integer multiple of the second. For instance, 3 times the period that we estimated for Planet 9 is about equal to the period of Sedna. We also found 4 other objects, I believe it was 4 other objects that are also in resonance. So the fact that you have so many of these parameters that are pointing in the same direction, in the estimate that we chose, the way we calculated the relative angular momentum, we also found that value of relative angular momentum compared with the same value, the same parameter for all of the asteroids was also very close. And it was 12% of the mean value. We're getting very close agreement with a number of parameters. That's, I guess, what convinces me is that it's just too big a coincidence for all of this to agree. It's just too big.
Yeah, it does not seem likely that it would agree without a giant planet causing it. It's the simplest explanation.
We also did confidence intervals for a lot of these parameters where we could. So 95% confidence intervals with classic statistical processes. We also, don't forget, we did a simulation too. We actually simulated all this. We only used 4 bodies. We used the Sun and Planet 9 in Sedna and the other planetoid, which everybody calls Biden, sort of informally. Those are the 2 largest of the asteroids. And we got pretty good agreement in the way that they converge, although we only ran it for 40 million years, and we needed to run it longer, and we were running out of time. So, but we did get good agreement with the way it moves in inclination and the way it starts to oscillate as it converges. The plane in astronomy is really defined, the orbital plane is really defined by 2 parameters. One is inclination, the other is something they call the longitude of the ascending node. Well, the azimuth is also determined by 2 parameters. One of them is the same one, so it appears twice. But for all of those planes to exist, all 12 planes to be within 14 degrees, 1 sigma of each other, and the asteroid, the azimuth figures as well, and the angular momentum, and all those resonances, we think something is really driving something in a very consistent way. And we just don't believe that you would find all this if it weren't there.
Yeah, it doesn't seem that you would. It sort of consistency always points towards, the natural. And is it really that surprising that there would be another planet out there, or multiple planets for all we know? I mean, look at Sedna. Sedna's a minor planet, so why wouldn't there be something even larger?
That's right.
Now, in your simulations and the work that you did, does it tell you anything about what the orbit might look like? Is this thing in a highly elliptical orbit, or is it more circular, like a normal solar system planet? Is there any indication of that?
Oh yeah, that's actually embedded in something called eccentricity. The eccentricity of the orbit. It is eccentric. It is. The closest it comes to the sun is about 82 AUs. That's astronomical units. 1 astronomical unit is the distance from the sun to the Earth. And so it's quite a ways. It comes, even though it's an elliptical orbit, nowhere near as elliptical as the asteroids. Even though it is elliptical, it doesn't come very close. So, but it'll have a long, thin, fairly thin orbit. Although, for a planet, although nowhere near as thin as the asteroids. So it's not circular.
Can this object perturb objects out there and send them into the inner solar system? Could this be, I believe it was Dr. Richard Muller back in the 80s came up with an idea that there was a brown dwarf or a small star out there that would periodically disrupt comets and things and send them raining into the inner solar system and killing dinosaurs. Is this thing anything close to that ability, or is it just in the wrong place?
No, it just doesn't have the mass. It doesn't have the mass to do that. The angular momentum of Planet 9, as we calculated from all of our numbers, it seems to add about only 8% of angular momentum to the planets. The reason is because the mass is fairly small. It's got about the same angular momentum, actually, orbital angular momentum as Neptune. It's very close. So it doesn't have enough mass to do much. Now, I will say this. We did talk about this very briefly in the paper. We made the assumption that there's really no strong connection between, or let's say no close connection between any of the asteroids. But on the other hand, some of those asteroids have very small perihelia. And so it can happen. But there is an effect called the Kozai mechanism. It's a very subtle effect, and it's very unusual, but it's accepted. It's accepted by astronomy. What it says is that if you have an asteroid in orbit, and there's a small asteroid, small mass, and it's within a circular orbit of something fairly large, then it's very strange. But when these two things come together, they're perturbed in a systematic way. It's not random, but it can drastically change the orbit, but not the angular momentum in the vertical to the plane. It's very strange, but so it sort of mitigates the fact of something being ejected. Not to say it can't happen, of course, but it under a lot of these close encounters, since close to the sun, Planet 9 has somewhat of a circular orbit, where it meets the asteroids, because they're on opposite sides of the sun. So the Kozai mechanism semi-works. It helps to keep this whole system stable. But that's not to say that something can't be ejected.
My last question for you is related to actually finding it. Now, you guys give an estimate in your paper above what the visual magnitude of this thing should be.
Yeah.
And it looked like we're going to need a big telescope. Do you anticipate that there is an instrument in service right now that could find this thing?
Yeah, I believe it because Brown believes it. The one thing that is challenging is we don't really know exactly where to look right now. Although we believe we have a way to make this calculation. The way the orbit lays out right now, the perihelion actually falls in the constellation Libra. The aphelion, the furthest point away from the sun, falls in Taurus. So the two collection points that I talked about earlier, the two attractors, would fall in the vicinity of Taurus. So that would be where you would want to look. But what we did is when we estimated the mass, and by the way, mass was shown to be, and we have a rigorous calculation that says mass is proportional to the square root of all of the masses of the asteroids. We came up with a vector equation that can be transformed using all of the instantaneous positions of the asteroids to get a pointing direction. We didn't do it. It's a lot of work, but we think we know how to do it. And then we've both gone on to other things, but we believe we've laid out a way to do it very, very briefly. So yes, we believe the data does support getting a pointing direction.
Zeroing in on Planet 9.
I wanted to mention one other thing too. Mattia believes that this object might have most of its radiation in ultraviolet. I mean, the infrared. And so it's more difficult to see infrared objects from the ground. So it's his belief that you need something that's up in the sky to look for it. This next generation telescope that they're going to put up, the James Webb Space Telescope, is due out in about a year. It's March of 2021, as I understand it.
Hopefully. Hopefully.
Hopefully, yeah. It's been delayed several times, as most people know. But he also believes, Mattia believes that we got to get something way up there. He'd like to see something beyond Neptune, but that seems to me like a pretty big act. But at any rate, I believe this James Webb Space Telescope could find it. I mean, there have been infrared surveys made, and it's never shown up in one of those.
Now, why would it be so visible in infrared? You would imagine that it'd be a pretty cold object out there as opposed to visible light, right?
Yeah, it would just be reflected light. It's it is very cold. It is very cold, but it probably, anything I told you would just be a guess. There have been a number of researchers that have also thought that it would be primarily visible in the infrared.
Pretty dim that far out, no matter what you do, I suppose.
Of course, we don't know how far out it is either. You know, it depends. It depends on one of the things that's a shortfall of anybody's estimation, Brown's and ours as well, is the fact that the pointing has been estimated using asteroids that are close to the sun. What other asteroids are, because they're the ones we know about. So what asteroids are out there that might be pointing in a slightly different direction or change the dynamics? We don't know. We just don't know, because these are very long period objects.
Well, that seems to be a trend, though, with this story, is that as more objects out there are identified, they all seem to point towards Planet 9.
Right.
You know, it seems as that within a certain range there, they seem to find more and more of these objects that seem to be affected by this large planet. So to me, it seemed like at this point, it almost has to be there. You know, as we were talking statistically, it just seems like there has to be something that's doing this.
Yeah, I agree. As a matter of fact, when we were looking to add other objects into the analysis, basically we only looked at two criteria. It was the only thing we looked at because the original data set sort of pointed us that direction. We said, well, what's within an angular spread of the same direction that we're looking at? And let's go wider than Mattia and Brown. So we went to 125 degrees angular spread. And all of the objects so far have been relatively low inclinations, below 30 degrees. So we said, well, we'll open that up too. We'll open it up to 40 degrees, but we didn't find anything that high. So, and the other thing too is with our estimation process, we use mass pretty heavily in several computations. If the mass is too low, it just doesn't change the numbers because the mass of Sedna and Biden are so large. It just doesn't change the numbers. So in order for an asteroid to be useful in this estimation process, it can't be too small. It's got to have some heft to it. So that's another thing we were looking for. Is it massive enough to make a difference? And so we did find 6 additional asteroids that fell into that window, and we think we have better numbers. We think we have considerably better numbers. But back to your original question, though. Back to your question a little earlier. Do we think we've got the ammunition to find actual pointing numbers where they are? We think we have the outline of a method, but we have not done the work. And I can't say that we have it until we've done the work. So it's a matter of faith at this point whether we really have a methodology or not.
Are you pursuing that? Are you going to do the work?
we've thought about writing another paper and doing that, and we've both gotten busy with other things, to tell you the truth. I think we ought to. And we did mention it in the paper. We actually pointed, there's one equation, there's equation 31 that people have to go to and say, can I get the coordinates, instantaneous coordinates from that? And we believe the answer is yes. But we haven't done it, so we haven't done the work.
But you've laid the groundwork for somebody if they want to do the work.
yeah, and exactly. So whether we will get back to it, I'd like to, because I think we can help shed some light on that. Even though the asteroid sample we have are all near the sun.
All right, Robert. That was like I said, I think the thing is out there, and I think it's only a matter of time until it's found. But your work definitely puts us in the right direction. And thanks for joining us today.
Oh, it's my pleasure. Thank you for having me.
And if you guys do another paper on it, I hope you'll come back with us.
Okay. Thank you very much.
I think the enigma of Planet 9 is soon to be solved. In the coming years, new equipment will come online to help in the search and perhaps find it. Then we'll get to try to figure out what this planet is like. But I have to ask myself, with all of the mounting evidence that such a planet exists, what would happen if in 100 years or 200 years we still haven't found it?
John, you haven't told the viewers to subscribe for ages.
Like, subscribe, and share.